Okay, we are jumping into a new set of material. We're going to chapter 6, and we'll do 6.1 through 6.4. So 4 sections in chapter 6. And then 7 we might do an activity with, but we're not gonna, it's not like stuff that's straight on the test, but we use stuff out of chapter 7, so I still like for us to talk about it. And then 8.1, 8.2, 8.3, 8.4 will be the other ones on the test. So test 2 will have eight sections of material on it. Okay, so it slows down after test 1 as far as the number of sections we cover. Okay. And then it slows down even more with the third test. The third test is 10.1, 10.2, 10.3, 10.4, and 12.1 and 2. Okay, so it really only has 6. Yeah. Okay. So that means the frequency of homework assignments will slow down too, or the Hawk assignments slow down too. So take a look at that. Okay. All right, so moving into chapter 6, what we're dealing with here is we're dealing with a new type of probability distribution. So in chapter 5, we worked with the binomial distribution. The binomial distribution is what we call a discrete probability distribution, because with binomial variables, it only takes on certain values, of the variable. So we have discrete data we're working with there. With the normal distribution, that is not the case. Okay? With the normal distribution that we're going to learn about in this section, we're dealing with continuous data. Okay? So our variable now is not a discrete random variable, it's a continuous random variable. Okay? Same idea, just different type of data. So we just have a variable that we know is going to represent a continuous number, continuous value, and then its numeric value is determined by the outcome of a probability experiment. So same idea as chapter 5, except we're dealing with continuous data. So that gives us some benefits, and it also poses some new challenges, switching from discrete to continuous data. One thing to remember about probability distributions, we got a little memory booster slide in here. And that's that no matter what probability distribution we're working with, and remember we had those two properties. One was that each probability is between 0 and 1, and that's true. But also this one, okay, that if we add up all the probabilities, we have to get 1. That's true of a normal distribution as well. Okay, so keep that in mind. And we'll look at the properties we have to have in order for a probability distribution to be considered a normal distribution. Okay. So remember with the binomial, we had like 9 things. We've got these 4, okay, with a normal distribution. So in order for a probability distribution to be a normal distribution, first of all, we need to be dealing with continuous data. So it says we have a continuous random variable. And then it says our distribution is defined completely by its mean and standard deviation. We'll see that again in a second. And then we've got these 4 properties. So number 1 is a nice property. It says a normal distribution is bell-shaped. We've seen those some, right, with the empirical rule. And symmetric about its mean, that just is saying that the mean is going to be in the middle. And if you look on each side of the mean, it looks like a reflection of the other side. And so symmetric about its mean. So bell-shaped and symmetric, that's the short version of that. Number 2 tells us a normal distribution is completely defined by its mean, mu, and standard deviation, sigma. So those are the same symbols we've used for population mean and population standard deviation. Nothing new there. The idea here that our distribution is completely defined by those two numbers, what that's saying is that if we know those two numbers, we know everything else. Okay? So if we need to know anything about a normal distribution, we can figure it out as long as we know the mean and we know the standard deviation. Number 3 was our memory booster slide there. It says the total area under a normal distribution curve equals 1. True for any probability distribution. And then number 4, we're getting a little theoretical here, but it says the x-axis is a horizontal asymptote for a normal distribution curve. Anybody remember what an asymptote is from algebra class? What was it? It was a line in the graph. How did the graph behave around that line? It gets close to it, but it doesn't touch it. It doesn't cross it. Right? It just gets closer and closer and closer to it. Okay. So I say that's a little bit theoretical. It depends on the context here, because what that's saying is that our normal distribution curve goes forever in both directions. It's saying it goes all the way off to negative infinity on the left and goes all the way off to positive infinity on the right. That's weird in practice, depending on the context. Like if we go back to one of those empirical rule problems, if we're thinking about the weights of babies, once you get down to 0, it doesn't make sense to go any further to the left, right? Because you don't have negative weights. But in theory, the curve goes that far. And also, that might be a little weird if the only time you might have seen something like putting number 3 and number 4 together is if maybe you took calculus somewhere. So we have an infinitely long curve, but the area underneath it is 1. That's a little mind-bending if you stop and think about it. Okay. You'd think the area would be infinity. It's not. Okay. Questions on any of those properties? Okay. So let's see one of these things. Okay. We've been drawing it, and we just haven't specified that's what we were dealing with. So we have a symmetric bell-shaped curve. Okay. And then we really only care about drawing it out so far. Okay, right? Technically, it goes all the way to infinity and negative infinity. But it's mostly the part around the mean that's useful for us. Okay. So our mean is the number right in the middle. It is symmetric, so the mean's in the very center. And then what else is in the center if it's perfectly symmetric? We got the mean, the median's there also, so half the area's on one side, half the area's on the other, and then that's also the mode, right? Because that's the tallest peak on the graph. Okay? Just a little review. And then down here, we've done this type of thing when we did empirical rule. This is just saying it's marked off in standard deviation. So here's the mean. We add a standard deviation, add another one, add another one. This one goes out 4 standard deviations. That's what a normal distribution looks like. Okay. All right, let's consider something though. We usually always draw a picture that looks pretty much exactly like this. Okay. But the scaling's not always exactly like this. Okay. In practice, sometimes we'll have like a short, really wide normal distribution, that's okay. Or we could have a really tall, skinny normal distribution, that's okay too. We normally don't draw them that way because it's easier to work with one that's kind of somewhere in the middle like this. But let's make a comparison here. Okay. So here we've got 3 different curves here, if you will, 3 different normal distributions. A is on the left, B is the middle green one, and then C is the one on the right. and we want to think about what the differences between these three are. I got a few questions to ask you. Okay. So the first one says which distribution has the smallest standard deviation and which one has the largest standard deviation. We can get that from the graph, so let's start with the largest. Okay, which one has the largest standard deviation? You remember what that looks like on the graph? Standard deviation is how spread out our data is. So which one's the most spread out? C, yeah, it's squished and spread out. So C has the biggest standard deviation. And then which one would have the smallest standard deviation? A gets the most squished this way, squished horizontally. And then B somewhere in the middle. Okay. All right, something else to think about here. Which one has the smallest mean? Which one has the largest mean? So how are we going to know where the mean is on these? We said with a normal distribution, it's right in the middle. It's right at the tallest peak. It's the same place as the mode. So like, here's the mean on A. Here's the mean on B. Here's the mean on C. And if this is a number line, down here, so smaller values are on the left, larger values are on the right. So which one would have the smallest mean? That'd be A, that's the furthest to the left. And then C has the largest mean, furthest to the right, and then B somewhere in the middle. Okay. We don't know what the numbers are, but we know small's on the left, big's on the right with a number line. Okay. And then the last one, we want to think about the whole data set. Okay. So like the blue curve, right, represents the whole data set of A. Right? Like we got some values over here and most of it's in the middle, and then we've got some that come all the way up here. With B, we've got some data values over here, most of it's in this area, and then we have some that come up here. So what this last question asks us is, looking at the position of A and the position of B, what does that tell us about the data values in each data set, like as far as their sizes? Since most of A is over here to the left of most of B, right? B's to the right of A, you could say that also. If we were looking at our data values, which one would have, in general, would have bigger data values? Let's ask it that way. B, because most of the data is farther to the right. And then we could say most of the data values in data set A are smaller than the ones in B. Okay? Just a little bit of thinking there. All right. Something else to think about. Let's look at this next thing here. This one says determine if the following distributions could be classified as normal distributions. Okay, so we have to think about those properties, what's required. A is this data that's ratings for customer service taken from an online survey based on a scale from 1 to 10. So do you think that one could be a normal distribution? I'm going to say no, and why? What about it? You're on the right track. What about our data values there? So let me back up a little bit. What type of data do we have to have a normal distribution? It's quantitative for sure, okay? And then it also has to be continuous. It's got to be continuous. You know? Got to be continuous. So what about our data here? If you have a survey, yeah, it stops at 10, and also what about in between? That's the thing. Yeah, it's more than one, but our individual data values in between, they're all going to be, you give somebody a 2, you give them a 5, you give them a 7. But if you're filling out a survey, you know, you're putting a number down, you normally don't get to put down like 1.75 or something, right? If you go on Amazon and you're doing a product review, you don't get to give it 3.5 stars. Right? They either make you give it 3 or make you give it 4. Now they take an average of that. That's what you see, but you only get to give it certain values. And so this is discrete data and discrete data. So it can't be normal distribution. Okay. What about B? We've got finishing times in minutes for runners in the Labor Day 5K race. What type of data is that one? It's quantitative and then it's continuous. We're measuring. Okay. It's in minutes, but we could use decimal places there. Right? And normally we would use seconds instead of going to decimal places for minutes. Right? Usually we go hours, minutes, seconds, and then we do decimals of a second, right? If we're racing, it's usually how it goes. But we could do it with minutes. We could say somebody 5K. I don't know what 5K times are. So we could say, you know, somebody finished in 18.1 minutes, and that makes sense. Or we could say somebody finished in 19.125 minutes. That makes sense. We're measuring time. So this is continuous data. So it could be a normal distribution. Could be. The thing to take away there is if we have discrete data, it's not going to be a normal distribution. Not much more in this section. It's a really short section. So one other little memory booster here. Okay. Getting us ready for the next section. We already mentioned it, and that's why it's a memory booster. We're saying it again. Okay. If we have a probability distribution, any probability we come up with has to be between 0 and 1. It can be 0 if something's impossible. That's 0. It can be 1 if something's absolute certainty. That's 1. Okay. It's got to be somewhere in between there. Okay. Questions on any of that? Short section. Just a little intro. Let's see. I'll keep. Okay. 6.2. Okay. We're dealing with one particular normal distribution. We have one that we like to work with. There are infinitely many normal distributions. Okay? Because remember, the thing that defines a normal distribution is its mean and its standard deviation. So you can come up with any mean you want to, positive or negative, doesn't matter. You can come up with any standard deviation you want to. So any standard deviation has to be 0 or bigger, right? But any standard deviation you want to. And if you come up with those two numbers, there's a normal distribution that fits those two numbers. Okay? So there's infinitely many normal distributions. Instead of having to work with all those infinitely many different curves, what we do is we've picked one that we like to work with, okay, and that's called the standard normal distribution. So what's special about the standard normal distribution? Okay. So before we get into that really quickly, something else we need to remember, okay, that we've already seen. We saw a z-score formula or a standard score formula. Remember what that formula looked like? It was a z is x minus mu divided by sigma, that formula. And the number we get out of that tells us how many standard deviations our x value is away from the mean of its distribution. We didn't call them normal distributions before, we just said symmetric and bell-shaped. So remember that thing, and then remember when we're calculating these, oops, sorry. Did I skip over a slide? I don't know, I don't know what happened to my other slide, but remember when we're calculating a z value, we're going to round to 2 decimal places, and you'll see why in just a few minutes. Okay. So what makes a standard normal distribution special? What makes it the standard? Remember, to define a normal distribution, we have to pick a mean and a standard deviation. So what we've done with the standard normal distribution is we've chosen a mean of 0. That means the middle of our curve is at 0. And then the standard deviation is 1. That's arbitrary. We could have chosen anything to make the standard. Well, it's not completely arbitrary, because what we've done is we've just picked easy numbers. Just picked easy numbers. So it's nice to have a mean at 0, because then if you have some value that's positive, you know it's above the mean. If you have a negative number, you know it's below the mean, without having to think very much. And then having a standard deviation of 1 just makes things easy for us. 1's a nice, easy number to work with. And the rest of this these are just the same properties that apply to all normal distributions except for number 2. Okay? So bell-shaped and symmetric, that's all normal distributions. Total area under the curve is 1, that's all normal distributions. X-axis is a horizontal asymptote, that's all of them. But the thing that makes the standard normal distribution the standard normal distribution is that it has a mean of 0 and a standard deviation of 1. Okay? That's our standard there. Okay? And the idea behind what we're going to do is, instead of having to work with infinitely many different normal distributions, what we're going to do when we want to deal with something that has a normal distribution, we're going to take and we're going to transform it, and we're going to squish it or stretch it or slide it around on the number line to make it line up with this standard normal distribution. And then once it does that, we can just work with the standard normal distribution instead. Okay? That has nice, easy numbers. And that sounds complicated. Like maybe we've got a normal distribution that has a mean of 185 and a standard deviation of 27.5 or something not real convenient. Okay? So we could draw the curve and have that normal distribution, but what we want to do is we want to squish it or stretch it or whatever we need to do, slide it over to make it line up with the standard normal distribution so we can work with it instead. And again, that sounds complicated, but it's actually easy. It's actually easy, because the way we do that is we just take all the data values out of our normal distribution and run them through this formula. So this little easy formula where we subtract one time and divide one time takes a data value and changes it to a z-value, and this z-value is just a number on the standard normal distribution. That's why we call it a standard score. So this nice, easy little formula is really, really useful for us. It does this big geometric transformation on any normal distribution we want to work with and turns it into, makes it line up with the standard normal distribution so we can just work with it instead. Okay? So you saw how we had the let me go back to that actually. Okay, one moment here. Let's look at that slide we had in 6.1 again. Maybe. And we had this slide where we had different normal distributions that had different, they were spread out differently and there were different heights and things. Okay. So if we think about B as being our standard normal distribution and the normal distribution we're working with is A, what we would have to do is we would have to take it and slide it over so that the means matched up. And then we would have to squish it to make it spread out until it lined up with the green curve. Or if we wanted to work with C, we'd have to take and slide it over to the left till the means lined up, and then squish it from the outside in to make it taller and make it line up with the green curve. That's what we're doing, but it's easy because all we have to do to make that work is use this little formula. Z equals x minus mu over sigma. Okay. Math people, that's something to get excited about. Okay? I know if you're not excited, I get it. Okay? That's something to get excited about because we have our everything happening here. We have something that's easy. That's also super useful. Okay? Usually, if you run into something that's easy, it's really not that helpful. Or if you run into something helpful, it's really hard. Okay? But this is a nice case where it's easy and really helpful. Okay, so let's look at how this is going to work, kind of. Okay? Let's look at this. So this gives us numbers for a normal distribution. It says consider a normal distribution with a mean of 48, standard deviation of 5. What we want to do, we're going to sketch out that normal distribution. Okay? And then it says convert an x value of 45. So this 45 is a number in this normal distribution with a mean of 48, standard deviation of 5. And we're going to convert that to a z value and then see what that looks like on the standard normal distribution. Okay. So the way we do that, this is our x, right? And there's our mu, and there's our sigma. Okay. So what we're given is that there's some normal distribution. It has a mean 48, so that's the number in the middle, and a standard deviation of 5. Okay. And what we want to do is we want to take some data value out of this thing. It says the one we want to look at is 45. So here, if 48's in the middle, which side's 45 going to be on? It's going to be a little over to the left, and it's not quite one standard deviation away from the mean. One standard deviation away from the mean would be 43. So it's not going to be super far over. It's going to be like somewhere in here. Right? So we've got some data value like maybe somewhere in this area. We're not being exact. We're just being approximate here, but here's our x. Okay. So what our formula does for us, we take that 45 and plug it in for x, and we would subtract the mean of 48, divide by the standard deviation of 5. And we're going to round to 2 decimal places. So then if we do, we'll get negative 0.60 once we round. So what that lets us do is instead of dealing with that normal distribution, we can deal with the, not my best drawing there, we can deal with the standard normal distribution. The mean of the standard normal distribution is 0, with a standard deviation of 1. And sorry, it's so low on the screen for those of you in the back. And so now on our standard normal distribution, this x value of 45 is going to be 0.6 standard deviations below the mean. Okay? So we end up with this new value. Okay? So negative 0.60. Okay? So I don't have it drawn to scale well. Okay? But what's happened is we've taken this normal distribution, it would be like over to the right of this one, right? Because its mean's 48. So if we had them on the same number line, our standard would be like right here, and then the normal distribution we started with would be over to the right. So we've taken it and slid it over to the left to make its mean match up with 0. Okay? And then the other thing we've done is our standard deviation was 5, so it was spread out some certain amount. But now we've changed our standard deviation to 1, so we've taken it and squished it to make it line up with this curve. And we can do that no matter what mean and standard deviation we start out with. So why do we give a rip? Okay. Why do we care? Why don't we care? Because again, okay, our point here is instead of having to know a ton of information about infinitely many normal distributions, okay, we can focus on just knowing one normal distribution really well. Okay? So we can just focus on the standard normal distribution, and everything we learn about it applies to, we can make it apply to infinitely many other normal distributions. Okay? That's our point there. Okay? And the first thing we're going to do with them, okay, we've actually used it a little bit already, right? Like when we had that test score comparison problem, had the 2 calculus students that were in 2 different classes and they were wanting to compare their test scores to their peers. What we were doing with that is we were saying where on the standard normal distribution does this test score fall, where does the other one fall, and then which one's higher. We didn't think about it quite like that yet. We weren't quite ready. Okay? That's what we were doing. But in this section, okay, really in this chapter, okay, what we're focusing on is we're focusing on finding different areas underneath these curves. Okay? Specifically today, we're looking at finding different areas underneath the standard normal distribution curve. Okay, so we're going to look at problems like this one. Okay. That one. Okay. This one says find the area under the standard normal curve to the left of a z-value of 1.37. If we want to know the answer to something like this, we have 2 options. Okay? Probably more than that, but we have 2 big ones. Okay? Option number 1 is there's a formula that tells you how to draw the graph of the normal distribution curve. I should have put it in the slide so you could freak out for a second, but I didn't, because it's not pretty. But there's a formula that tells you how to draw the curve, graph the curve, and then you can use calculus to calculate the area underneath the curve. Okay? I'm guessing that's not the option most of us want to use. That's not the option I want to use either. Okay, so our other option is to use some tables. So these are mine. I'll let you use them in class. Okay, so we'll use them almost every day from now on. Okay, so if you will, I'll pass them out every day, and then you can just leave them like on the table up at the front as you go if you don't mind. That way you always have one. You don't have to worry about forgetting it. Okay, I'll post them on Canvas if you want to print them out, if you want to have the printed versions. There are electronic versions in Hawks, but if you like having the print to look at better, then it's just 2 pages. So I'll post those on Canvas. Okay, but I will let you use mine during class. You're welcome. So if you will, try not to write on these. I know you forget sometimes. So today, that's what we're focusing on. We're going to use these things to figure out areas under the curve. You're welcome. There you go. Welcome. All right. So before we can answer this question, we have to look at and figure out what information our tables actually give us. Okay, so if you'll, that's on both sides. Let's start to say if you go to side A, okay, but I think it's on both sides. It tells us numerical entries represent the probability that a standard normal random variable is between negative infinity and z, where z equals x minus mu divided by sigma. Okay? If that's not very clear to you, that's okay. That's pretty confusing. Trying to figure that out all at once. Okay. After you know what it's giving you, it makes sense why they wrote it that way. But first seeing it is confusing. So luckily, we've got a picture. Okay. It's on two different pictures, but they're the same idea on both sides of the table. Okay. And it shows the curve, and then it shows it shaded to the left side of a z-value. So what our tables give us, they're giving us the area to the left of whatever z-value we look up. Okay. Okay, so our tables give us area to the left, or the way they word it, and you'll see it in Hawks when you are picking, like in Hawks, it gives you two different buttons for the two different sides of the table. It's really all one table. It just all won't fit on one page. But what we're given the area from negative infinity to z. Right? That means all the way to the left, all the way from the left, all the way up to z. So that's the area to the left. Okay. That's what our tables are giving us here. Okay. And in Hawks, one table says negative infinity to z. The other one says negative infinity to negative z. So all that is, if you look on side A, if you look down the column on the left, you'll just notice that all the negatives are on that side. And then if you flip it over, all those are positive. That's all this is, okay? So this is just the side of the page that has the negative z-values. This is the side of the page that has the positive z-values. Okay? Nothing, no big deal there. Just because they wouldn't all fit on one page. Okay? So, to answer this question, it says find the area under the standard normal curve to the left of z equals 1.37. Our tables give us area to the left, so all we have to do is look up a z-value of 1.37. Okay. So these tables are a little weird to get used to. So if you look at it, if you look down the left-hand column, it gives you the first two digits of the z-value. And then if you look across the top, what it's giving you there is the last digit, the third digit. Okay. So what we're going to want to look for is we're going to want to look down the left-hand column for 1.3. Okay. And then we're going to want to look across the top for 0.07. And we'll look for that last digit there. Okay. So that's on side B. Okay, you don't have to think about that, but it's on side B. And if we look at our table, okay, we'll find so you go down the left until you get to 1.3, and then go across until you get to the column that ends with 7, right, for 1.37. And then we get our area, 0.9147. Okay. So what that's saying is that we go to a z-value of 1.37, 1.37 standard deviations above the mean of our standard normal distribution. Then from there to the left under the curve, that area underneath this curve here is 0.9147. Okay. And it's not like a square, right? So we can't do length times width. Okay. So that's why we would have to do calculus if we were trying to figure it out the other way, because we're trying to figure out the area underneath the curvy thing. So that's a calculus topic, but the tables work just fine. Okay, tables work just fine. Questions on that one? May I have trouble finding it on the table? You're going to be professional table readers by the time you get finished with 204. Okay, so sorry about that. Just remember, if you get tired of looking numbers up in the table, remember the alternative is to use calculus, and then it makes it not so bad that you're looking a number up in the table. Okay. Let's look at another one. There's our area. Okay. All right, this one says find the area under the standard normal curve to the left of a z-value of negative 2.03. So we're going to look for negative 2.0 down the left side. And if you're on the wrong side, right, you'll look and you'll see the z-values are positive, so you know you got to flip over to the other side. And then we look down the left-hand column for negative 2.0. And then we're going to go across the top until we get to the one that ends with 3 to get our last digit. Okay. So down to negative 2.0 over to 3, and we get 0.0212. Should find there. Have trouble finding that one? Got the idea about how to read the table? All right, so, and then again, it's good to keep in mind the picture of what we're finding. Okay? So we're saying if we pick a z-value, this z-value negative 2.03 off the standard normal distribution, and it's a little further over, right, because it's a little bit more than 2 standard deviations below the mean. Right? Then the area from there to the left is 0.0212. Okay. Something that can help you check your answers and make sure you're on the right track. Right now, it's not a big deal. It'll make more sense in a minute while I'm telling you this. Okay, but something you can kind of use just as like a sanity check, and to make sure your answer is, you know, not just completely out of the blue. Okay? Keep in mind that we're symmetric. Okay? So, like if we have a z-value that's on this side, right, on the left side. Well, let's think about this. I'm wording it poorly here. So if we go to 0 and we want the area from 0 to the left, what's that going to be? Our area. It's a negative z's, you're right. But what's the area under the curve going to be if we start at 0 and go to the left? You can think about it as percentage. What percentage of our area is from the middle to the left? Okay, let me back up. What did we say our shape was? Symmetric, yes, bell shape, but it's symmetric. So what percentage of the area is on each side? 50. Okay, so if we go from 0 to the left, that's 50%, or in decimal form, 0.500. Okay. So what I'm saying as a sanity check, okay, is that since this one was over here on the left, we knew we were going to have less than half the area is our answer. So like if we'd ended up with 0.8 or something, we would know that we messed up somewhere because we're expecting less than 0.5. On our other one, and on our first one, our z-value was over here past 0, right? It was on the right side, and we were going to have more than half the area, so we expected it to be more than 0.5. So just to, you kind of think your way a little bit through that before you even look the number up, then that kind of can help you make sure you're not getting something mixed up. Okay. All right, so just a little thing to mention there. Okay. That's area to the left. Since our tables give us area to the left, finding the area to the left of a z-value is the easiest scenario. That's the easiest scenario. We just look it up, table gives us the answer. But we don't always want to know the area to the left of something. Okay. So let's look at another one. This one's a little different because this one says find the area under the standard normal curve to the right of 1.37. So a big difference. Because our tables give us area to the left, of whatever we look up. This one wants us to find the area to the right of some number. So there's two ways we can go about finding this with our tables. Anybody have any ideas? Any thoughts? Go ahead. What are you saying? Subtract it from. Let's go ahead. I think we're getting there. All right. All right. So let me back up to our memory booster slide I skipped over. The area under the whole curve is 1. All right. So one way we can work these if we want the area to the right. So here's our picture of a poorly drawn picture of what we want. Here's some z value that we're looking at, 1.37. We want this area, but our tables give us area to the left. So our tables would give us this if we look at 1.37. So how can we figure out the red part if our tables give us the blue part? We got to think about that the whole thing's 1, right? The whole thing's 1. So to find area to the right, we could say 1 minus the area to the left. And that'll give us area to the right. So that's one option. That's real similar to what we did with those probabilities with the binomial. If we wanted the probability of greater than, right, we had to do 1 minus the opposite because we knew the whole thing was 1. So that's the same idea here. It's called the complement rule. Okay. So on this one, if we wanted to do it that way, okay, we would look up 1.37 in the table, and that's going to give us this area, the area over here on the left. So we'll go to our table and look at 1.37. Yeah, we got 0.9147. Then we could subtract. See what we get there. Have I done it already? Let's see. 1 minus 0.9147. That gives us an area, a point, and I'm going to do it in red because this is the red area. Okay. 0.0853. That's the one we want. Okay. So we wanted this one. We know the whole thing's 1, so we can do 1 minus this one to figure out our missing piece. So that's option 1. That's option 1. Okay. We've got another property of our curve we could use to do it a different way. You may think of some other way we can do it. What else do we know about our curve? We know the total area under the curve is 1. What do we know about the shape? It's symmetrical. Okay, so here's something else to think about. Okay. So here's our curve again. And we want this area, right? We want the area to the right of 1.37. Since we know our curve is symmetric, that means there's another z value over on the other side, negative 1.37, because the center's at 0, right? So it's going to exactly match up, just the opposite sign. And the area to the left of that z value is going to be the same as the area to the right of the positive one because it's symmetric. Right? So since these numbers are at the same place, just on different sides, this area has to be the same as this area. So instead of looking up 1.37, we can look up negative 1.37, and we'll get this area, which is the same as this area. Okay. So if we go to negative 1.37 and look it up, yep, sure enough, we get 0.0853. And since this thing's symmetric, that means this one over here is also 0.0853. Okay. Make sense? You can do them either way. I don't care which way you do it. My suggestion is that as you're working on this assignment, try it a couple ways, try a couple both ways, and then see which one you like the best, and then stick with it so you don't get confused. Okay? So option number one, if we want area to the right, is we do 1 minus area to the left. Option number two, if we want area to the right, is we can look up the opposite z-value. Okay? Look up the opposite z-value. And so if it gives us a negative, we would look up the positive. If it gives us a positive, we would look up the negative. It's just the opposite. Opposite for area to the right. And as we go through this stuff, usually you can think about right meaning opposite. So that comes up a lot, this situation, where if you want something to the right, you do the opposite. Right? Let's look at another one. What's next? Okay. That's all just saying the same stuff we talked about. Okay. Look at this one. This one says, find the area under the standard normal curve to the right, negative 0.90. So either we can look up negative 0.90 and do 1 minus the answer we get, or we can look up the opposite of this. So we can look up positive 0.90, and that will be our answer. You don't have to do both. Okay? Sometimes people make the mistake of doing both things. Okay? And that ends up with the wrong answer if you do both. They can do it either way. I'll do it both ways. Okay? I'll give you a chance to look at it. Okay? So option number one. Okay, is we can find this area. I guess if we look up negative 0.90, that's 0.1841. And then we'll do 1 minus that. So 1 minus 0.1841 equals, do my calculator. .8159. This area. Okay. That's option one. Okay. Option two, we can look up opposite. In this case is positive 0.90. We do that if we look at positive 0.90, hopefully we get the same thing. Yeah, we do, we get 0.8159. Okay. So either way works. Okay. Most of the time, people end up doing it this way. That's how the majority of people do it. Some people do it the other way. Okay? One way is not better than the other. Maybe I'm a little bit lazier. I tend to do this way because I don't have to subtract. Okay? But for some people, this keeps it in their mind what they're actually doing. Like keeps the picture in mind better than just having a rule. Either way's fine. Either way's fine. So far we've done 2 different types of area. We have a total of 4. Here we're going to do. Okay, so type number 1 is area to the left of a z-value. That's the easiest. We just look the z-value up in the table. Okay. Type number 2, if we want the area to the right of a z-value, either we do the complement rule or we look up the opposite. Either way there. Okay. Okay. Questions on those? I know it's not real exciting learning how to look up numbers in the table, but we're going to use it a whole lot. Okay, so really important to practice this section so you get comfortable with it, because it'll just make everything else easier to go along. Okay. All right, next. I left a lot of the textbook stuff in here. Oh, no. There we go. Went too far. Okay. So our third type of area we're going to find is the area between 2 z-values. Sometimes we want to know those. Okay. So here, this one wants us to find the area between negative 1.68 and 2.00. So as a picture, here we got negative 1.68. We're over here, we got 2.00. And we want this area, the area in the middle. How can we do that? So keep in mind our tables give us area to the left. Okay. Tables give us area to the left. So the idea here is if we look up 2.00, that would give us the area from here all the way off to negative infinity. Okay. That's more than we want. We don't want this extra piece on the left. Okay, we would call that the left tail. And when you get out to the edges, we call those the tails. Okay. So we don't want this piece. Okay. But it turns out if we looked up negative 1.68, that would be the extra that we don't want. It would give us the area from there to negative infinity. So what we can do is we can look at this area and chop off this area, and we get the area we want. So how can we do that chopping off? What? Subtract, yeah. So our math operation for getting rid of something is subtraction. So here's a better picture. Okay. If we look up a z of 2.00 in the table, gives you 0.9772, but that's more than we want for our final answer. Okay? That goes all the way off to negative infinity. But if we look up negative 1.68, that gives us, this is not a negative area, this is saying subtract the area. Okay? It gives us 0.0465. That's the piece we want to get rid of. So we do 0.9772 minus 0.0465, and that gives us the area between the two, 0.9307. Question on how that's working? Okay. So what can go wrong trying to do that? So it's easy to say you look them both up and subtract, but you have to be a little bit more careful than that, because if we subtract 2 numbers, does it matter what order you put them in? Yeah, 3 minus 2 is not the same as 2 minus 3. Yeah. But, okay, so all right, let me, for the big but, okay, how do we know which one to put first? The one to the furthest to the right or the bigger one, yeah. So, And you don't even have to think about the z-values if you don't want to. You can wait until you find both the areas and put the biggest area first, because we want our answer to come out positive. Because remember, we're dealing with area. Okay? That's a two-dimensional value, area is. And with area, we can't have negatives. Okay? No matter how small your house is, okay, you don't have a negative square footage house. Okay? You can't have a negative 1,500 square foot house. Area is always either from 0 or bigger. Okay, so that's got to come out positive. So either you got to remember one of two things. Either you got to remember to put the big area first when you subtract, or if you don't even like that, think about what happens if you switch. And this is something you might not think about, thought about before, but if we put them in the opposite order, we get them backward. How does that play out? For sure, we're going to get a negative, right? Because we're subtracting a bigger number than we started with. But what? Yeah, because what do we get? We get negative 0.9307. Okay? So as long as you remember area can't be negative, you don't even have to worry about it, what order you put them in. You can just put them in and know your answer's got to be positive. Okay? So either thing, remember your answer has to be positive, or remember that to put the biggest one first. Okay? Either way works. Okay? So here's our review as we go. Okay? Area to the left, you just look that z-value up. Okay? Area to the right, you either do the complement rule, subtract it from 1, or you look up the opposite. Okay? And then area between two z-values, you look up both the z-values, subtract the areas, and then either your answer's got to be positive, right? So either remember you got to put the big one first, or that just your answer has to be positive. Okay? Let's do, I think I got one more of these. Yeah, we've got one more between here. So let's actually think. No, we don't. Okay, so between we just subtract. Okay. Sorry, I thought I had another one in here. Okay, last type of area. Okay, we're on about to go to type number 4 here. Okay. This one's a little weirder. This one says find the total of the areas under the standard normal curve to the left of negative 2.50 and to the right of 3.00. Okay. So what's happening here, if we make our little sketch, okay, this is saying we're going to go to negative 2.50, and we want the area to the left of that one plus the area to the right of 3.00, so plus this area. So what we're looking for is we want this area and this area put together. Okay? We want to know the total there. You could, but we don't have to work quite that hard. Yeah, you definitely could do that, and if that makes sense to you, that's fine to do it that way. Okay? But here, really, I think the little bit shorter way to think about it, it's not much shorter, but the little bit shorter way to think about it is this is really just two area problems. We want the area to the left of this one, so how can we find area to the left? We just look it up in the table. So if we go to negative 2.50, let's see what we get there. 0.0062 that I found. Then we want the area to the right of this one. Yeah, so the lazy way, okay, is to look up the opposite, look up negative 3. If I look up negative 3.00, I get 0.0013. That's it. And then we just want the total, so we just add these two together. So we get a total area, 0.0075. But definitely you can do it the other way you mentioned too. That's really good you saw that. Okay. The other way that was mentioned, okay, because she didn't hear, was finding the area between, just like we did on the last one, and then do 1 minus that area. All right, because the area between is the part we don't want. So that works also. It's just one extra step, one extra operation. Okay. Because to find the area between, we'd still have to look them up. There we just add instead of subtract. Questions on that one? That's our 4 types. The area to the left, we just look it up. Area to the right, complement rule or look up the opposite. Area between, look them both up and subtract. Answer has to be positive. Area, this one we call area in the 2 tails. Okay. So these extreme outer parts on each side, when it gets skinny, we call those the tails. Right. So we want the area in the 2 tails of the curve. You add, look up, just find both areas and add them together. There is one other thing to mention, that, and it's not like that life-changing, this last thing we're going to see. It's a little bit easier than this, but it comes up so often, it's worth mentioning. Like, you know, if you have a little life hack that, and you say, well, that little life hack only saves me 5 seconds from doing it the way I normally do it. But if it saves you 5 seconds 10,000 times, then it's worth thinking about. Right? So that's kind of this last little thing. Let's look at this last one here. Look at this one. Okay. It says find the total of the areas underneath the standard normal curve to the left of negative 1.23 and to the right of 1.23. Okay, so same type of problem as the last one. But what do you notice about the z-values this time? Yeah, they're just opposites, right? They just have opposite signs. So the shortcut here, okay, at least the shortcut in thinking, okay, is that since we have, well, I'm going to call them symmetric z-values, since they're just opposite signs, we don't even have to worry about this side. All we have to do is look up this area and then do what? Multiply it by 2, because they're going to be the same. They're going to be the same. So in this case, and this comes up a lot, more often than not, when we want the area in the 2 tails, we have these symmetric z-values down the road. And so this does come up a lot. So all we have to think about is finding this left tail. Okay. So look up negative 1.23. That gives me 0.1093. So then to find the total, I just multiply by 2. Okay. What we get there? I got it. Get 0.2186. And if you forget that, it's okay, because what happens if you go to do it the other way? For this one, to find this area, you would look up the negative and you get the same number. 0.1093 plus 0.1093 is the same thing as 2 times 0.1093. So not a big deal. But it's just a little thing to think about. If you keep that in mind, saves you a little bit of brain power and down the road. Not much, but a little. Okay. Questions on that one? Okay. All right, so here's another why do we give a RIP moment? Okay? So we spent all this time finding these 4 different areas. Okay? So why do we care about these 4 different areas underneath the normal distribution curve? Okay? The reason why, and one reason why, okay, is that when we're finding these areas underneath the curve, well, hang on, one last time here. Okay? I got these 4 slides in. Okay? If you remember, if you need them. So area to the left, the subscripts didn't work, okay? And I couldn't fix it because this is how it came out of the book. Okay? You just look up the z value for area to the left, area to the right. Got you look up the opposite. You can't do complement rule. Area between, you look them both up, subtract. Answer got to be positive. And then area in the 2 tails, find both the areas and add them up. Those are our 4 types. Okay, so all right, back to why we care. Okay, when we're finding these areas underneath the curve, it's not just because we love area. Okay, it's because these areas underneath the curve correspond to something. Okay? And the thing that these areas underneath the curve corresponds to is probability. So let's look at this. Okay, this says, in probability notation, if we put this in words, this says find the probability of having a standard or having a normal random variable, standard normal random variable, because it's a z, less than or equal to negative 2.67. Okay, so that's a mouthful. Okay? But what that's saying is, like, we've got our standard normal distribution. What's the probability of picking a random value out of that standard normal distribution and it being less than or equal to negative 2.67? Okay. Okay, so the reason why we've cared about these areas is that this thing in here, z is less than or equal to negative 2.67, that's just telling us to find a certain area underneath the normal distribution curve. Okay. And this one turns out to be, here we would want the area under our standard normal distribution curve to the left, because it's less than, of negative 2.67. Okay. And we just figured out how to find that. Okay. We want the area to the left of a z value. We just look it up in the table. So negative 2.67 gives us 0.0038. What's the probability of finding a random variable less than or equal to negative 2.67, standard random variable? 0.0038. Okay. So now all of a sudden, instead of just finding areas, what we've done is we've developed a way to find different probabilities when we're dealing with normal distributions. Because all these we've done, we're finding areas underneath the standard normal distribution. But remember what we can do. We can take any normal distribution and make it match up to the standard normal distribution, right? We squish it and slide it and make it line up. Okay. So in that case, we'll see it later. Okay. And in that case, we'll see it next time. Okay. We don't have to just ask this question just about z's. We can ask about x's. So we can say, like, what's the probability that a baby born weighs less than some certain number, right? Then in that case, that's continuous data, okay? It's a measurement, and lots of things end up taking a normal distribution shape, okay? That's one of them. So then there, we could change that weight that we were concerned about into a z, and then look up the area or the probability in our tables. That's where we're headed. So before we can get there, we got one last thing, okay? One last thing to talk about, and that's which type of probability notation lines up with which type of area, right? Because we've got 4 different types of area. Okay. And then before we get there, I got one other thing. We're almost done. Okay, we got like 2 slides left, and we're done. Okay. So something to point out, and this is different than what we dealt with in chapter 5. Okay. Remember in chapter 5 we had the things like if we wanted the probability that x was less than 4, we could say, well, that's the same thing as saying the probability that x is less than or equal to 3, right? Because less than 4 meant the same thing as less than or equal to 3 because we didn't have any numbers between 4 and 3. And like maybe you got either 4 heads or 3 heads, you couldn't get anything in between there. We had weird stuff like that. Since we're dealing with continuous data here, we don't have that situation. Okay, we don't have weird stuff going on like that. Okay. And also, okay, another consequence of moving from discrete data to continuous data is this statement. Okay. So this thing's really nice for us. Okay. What this is saying is that the probability that a variable is less than or equal to some number is exactly the same as the probability that it's strictly less than. Okay. Or the short version of that, the part to get happy about, is that we don't care if we have an equal to bar on here or not. We don't even have to think about it, okay, because the 2 numbers are going to be the same. So now all of a sudden dealing with continuous data, that equal to bar is meaningless for us. Okay. So you can write it or don't write it, it doesn't matter. So that's nice. Give me 30 seconds to nerd out for a second on why that is, and then we'll go on to the last thing and be done. Okay. So why is that the case? Okay. It's a geometry issue. It's a geometry issue. So the only difference between these two, okay, there's the one on the left, there's the one on the right. The only difference between these two is the equal to part. So here we're looking for, on that one, less than, so it's area to the left. So there what we want is we want that area, okay? Do you remember what no, sorry, I messed it up. We want this area. Okay. We've got a solid bar there. Okay. And if you think back to algebra class, the only difference if you're graphing an inequality is that if you don't have the equal bar, you leave out the line. You have a dashed line instead of a solid line. So the only difference is that over here, we would not include the line in our calculation. So the only difference between the areas is whether or not we include the line, and a line doesn't have area. A line's one-dimensional, has no area, so it doesn't make a difference in our area under the curve. Okay? There's my 30 seconds. Okay, you can wake back up now. Okay, so last thing. Okay, which one of these notations means which type of area? Okay? We're going to need that for next time. Okay? So here we've got some in the slides. Okay, if you download the slides off Canvas and look at them, after this slide, it shows you how to find these different areas we've talked about on TI 83 or 84 graphic calculator. If you have one of those, I left them in there for you, okay, so you can follow those directions if you want to do them that way. You're also welcome to do them just with the table. Okay, either way's fine. Okay, so here, I'm not going to make us find all these areas. All I want us to talk about is which type of area the notation corresponds to. Okay. So on A, the thing to pay attention to is the way the inequality goes. Less than, if you take a less than symbol, turn that into an arrow, it points to the left. So here we want the area to the left of that z value. So we want the area to the left of 1.45. That's easy. Points to the left, you want the area to the left. On B, is we want the probability z is greater than or equal to negative 1.37. Remember, we don't care about the equal to bar. So all we care about is the greater than part. And if you turn that into an arrow, that points to the right. So for that one, we would want the area to the right. Of negative 1.37. C is a little weirder, okay, but what that's saying, if you can read it, then you can figure out which type of area we want. This says what's the probability that z is between, right? It's in between these two numbers, so what's the probability that z is between 1.25 and 2.31? So on that one, we just want the area between those two z values. Between. Okay. And then for this last one, guess which one it is? This is two tails, right? Two tails, because we've got two pieces. So this one says what's the probability z is less than negative 2.5 or greater than positive 2.5. So we've got two pieces. So that's the area in the two tails. Okay. These last two, I think that'll be good to start class with next time, okay? Because they're a little more interesting. Okay? So we'll stop there. Okay? Sign-in sheets going around. Okay, if you didn't get on it, we'll move it up to the front. You can get on there. I will see you Thursday.